Just beyond Pluto's orbit, beyond the Kuiper Belt's band of icy bodies, the Sun's domain stretches nearly a light year outward, into a realm no telescope has ever imaged. We know it exists because it sends long-period comets hurtling toward us, blazing across our skies after dark pilgrimages. This is the Oort Cloud, a spherical shell of trillions of icy bodies, the remnant building blocks of our solar system's youth. Each comet is a frozen archive, preserving the composition of the primordial disk that birthed planets. Tonight on Skyward Space Quest, we journey to the edge of our sun's reach to explore the origin, dynamics and mysteries of the Oort Cloud, our solar system's final frontier. In the early solar system, a swirling, flattened disk of gas and dust surrounded the newborn sun. Within this protoplanetary disk, dust grains stuck together built into pebbles, then boulders, and ultimately into planetesimals, the seeds of planets. Near the center, high temperatures drove off ices, favoring rock and metal, the inner terrestrial planets. Farther out, ices of water, ammonia, and methane could freeze, forming massive cores that accreted hydrogen and helium, giving birth to the giant planets. But not all planetesimals fell into orbits that became neat, circular, and stable. Gravitational interactions with the growing giants, Jupiter's massive pull, Saturn's resonances, Neptune's migrations, scattered countless icy bodies. Some flew inward as short-period comets, some were ejected entirely into interstellar space, and a select few were gently nudged into distant, loosely bound orbits tens of thousands of astronomical units away. Then, the galactic environment played its part. Passing stars and the subtle tidal pull of the Milky Way's disk nudged these distant planetesimals, randomizing their inclinations and circularizing their orbits into the near-spherical reservoir we call the Oort Cloud. Today, it stretches from roughly 2,000 to 100,000 AU, from the halfway mark of Voyager's journey to nearly the distance to Proxima Centauri. It is a ghostly halo, invisible yet gravitationally present in every long-period comet we track. Jupiter's role was paramount. Its immense gravity acted like a cosmic pinball flipper. As icy planetesimals drifted inward, close encounters with Jupiter could deflect their paths dramatically. Some were flung into the inner solar system, becoming the familiar short-period comets we see every few decades. Others were ejected to the fringes, destined for the Oort Cloud. Computer models show that without Jupiter, the Oort Cloud would be vastly underpopulated, its scattered members either plunging into the sun or being lost to interstellar space. Thus, Jupiter served as both a protector, shielding the inner solar system from too many comets, and a gardener, planting seeds in the Oort Cloud. We cannot see the Oort Cloud directly. Its members are too small, too distant, and too dark. But its existence is written in the orbits of long-period comets like Hale-Bopp and Lovejoy, whose orbital periods span thousands to millions of years. Jan Oort's 1950 paper demonstrated that new comets arrive from all directions, with a near-isotropic distribution. This randomness in orbital inclinations could only arise from a roughly spherical source. Spectroscopic analysis of these comets reveals water, CO, CO2, methane, ammonia, and complex organics, materials frozen at the solar system's birth. Sample return missions like Stardust and Rosetta's Philae lander have examined ices from short-period comets, but Oort Cloud comets offer a more pristine record, untouched by repeated passages near the Sun. Astronomers use long-term surveys, Catalina Sky Survey, Pan-STARRS, and soon the Vera Rubin Observatory, to catch these rare visitors. Each new comet expands our knowledge of the cloud's composition, structure, and the processes that send icy bodies hurtling inward. The Oort Cloud is not a static shell, it is a dynamic environment shaped by external forces. Passing stars every few million years, a star swings through the Sun's neighborhood at a few kilometers per second. Though distant, its gravity can dislodge Oort Cloud objects, sending swarms of comets toward the inner solar system. Studies of stellar motions using Gaia data help predict when past and future stellar encounters might have showered Earth with comets, or will do so. Galactic tides. The Milky Way's disk and bulge create a gravitational field that subtly stretches the Oort Cloud along the galactic plane. This tidal tug can nudge comets inward, though at a slower rate than stellar flybys. The combination of these perturbations dictates the flux of comets into the inner solar system. Some theories even link periodic comet showers to mass extinctions on Earth, though this remains debated. Each long-period comet is a messenger from the solar system's dawn. As it enters the inner solar system for the first time, ices sublime, dust lifts off, and jets sculpt intricate coma and tail structures. Spacecraft missions illustrate this treasure trove. Giotto flew by Halley's Comet in 1986, sampling its gas and dust. Stardust returned samples from Comet Wild 2 in 2004, revealing high-temperature minerals mixed with ices. Rosetta orbited 67P Churyumov-Gerasimenko in 2014-2016, mapping its surface, measuring outgassing, and deploying the Philae lander. But these were short-period comets. Oort Cloud visitors like Hale-Bopp may offer even more pristine material, preserving volatile ices lost to heat and radiation over short-period cycles. A dedicated Oort Comet Interceptor, a spacecraft waiting in a parking orbit near Earth to rush out to new long-period comets, could rendezvous and collect samples in situ, providing the first direct look at Oort Cloud ices. Touching the Oort Cloud itself is a challenge of distance and time, yet several mission concepts aim to probe its inner edge at a few thousand AU. Solar sail probes could accelerate to high speeds, using sunlight or Earth-based lasers, reaching 1,000–2,000 AU in 15 to 20 years. Upon arrival, they would image the faint inner cloud and sample dust and plasma. Nuclear thermal rockets promise faster transit, but require robust reactors miniaturized for deep space use. Comet rendezvous, sample returns target long-period comets as proxies, bringing back material without traveling to the cloud itself. Advanced interstellar precursor missions like Breakthrough Starshot's tiny laser sails may one day cross the interstellar boundary, offering a path to sample true Oort or interstellar objects. Meanwhile, Earth-based surveys with the Nancy Grace Roman Telescope and Vera Rubin Observatory will refine our census of inbound comets, allowing statistical modeling of the cloud's mass and distribution. In the coming decades, technology may allow humanity's first direct encounter with the Oort Cloud's frozen citizens, unlocking secrets of solar system formation and the distribution of water and organics across space. The Oort Cloud stands as the solar system's hidden frontier, a vast unseen reservoir of icy relics orbiting at the threshold of interstellar space. Its comets light our skies and carry the story of our origins, but its depths remain uncharted. As we refine our surveys, launch new missions, and harness emerging technologies, the day may come when we glimpse the cloud directly, sample its ices firsthand, and complete our exploration of the Sun's realm. This is Skyward Space Quest. If this journey to the solar system's edge stirred your sense of wonder, please like, subscribe, and join us next time for another odyssey through the cosmos.